This is part 1 of the end of year chemistry exam revision. One of the objectives that will be tested for this end of year exam is to calculate the average reaction rate using the rate of consumption of reactants or rate of production of products, with the equation average reaction rate is equal to negative change in the concentration of the reactant over time interval, or is equal to the change in the concentration of the product in a given time interval. Let us look at the sample problems in the next slide. Consider the reaction W produces Z. The average reaction rate is, recall that the average reaction rate, let me just write that down, or the average reaction rate is equal to the negative change in the concentration of the reactants, or divided by the time interval, or it could also be equal to the positive change in the concentration of the products in a given time interval. Again, it is very important that we note the difference. If we're looking at the concentration of the reactants, there has to be a negative sign. So looking at these equations, the correct answer would be the negative change in the concentration of the reactants over time, and that gives us, since the reactant is W, this is the reactant, therefore that gives us that the correct answer is A, the negative change in the concentration of the reactant, which is W, divided by time. So another answer would have been change in the concentration of Z divided by the time interval. However, we do not see this answer, because for B, you have the presence of the negative sign, which makes this answer wrong. But if it was positive Z, or positive change in the concentration of Z in a given time interval, then this could also be, this one here could also be a valid answer. But given again the choices that we have, we are left with A as the correct answer. Let's look at this question. In the reaction hydrogen gas plus chlorine gas producing 2HCl, the rate of reaction was studied and the result obtained are recorded in the table below. Calculate the average rate of reaction in terms of concentration of H2 consumed per minute. Since it is specified that we have to look into the concentration of the hydrogen gas, again it is specified here, then we will have to look into the details that are related to the concentration of the hydrogen gas. Now remember that the average rate of reaction is equal to negative change in the concentration of the reactants in a given time interval divided by T, or it could also be the positive change in the concentration of the products in a given time interval delta T. Now, since the hydrogen gas is part of the reactants, it is on the left side of the equation. Therefore, the equation that we are going to use should be this. And when we say negative change in the concentration of the reactants, we will have minus. Change in the concentration would be the concentration final. So the concentration final of H2 minus the concentration initial of hydrogen gas divided by time interval. Again, change would always be final minus initial. Let us substitute the values. So, and in fact, in our time interval here, it should be final time minus the initial time. Let us substitute our values now. We have the negative. The final concentration is 0.020 molar. So that would be 0.020 molar minus the initial concentration, which is 0.030 molar, divided by the time interval. So our final time is 4, and the unit here is minutes. So we will have 4 minutes minus the initial time. Alright, that's initial time, which is 0 minute. So 0 minute, and then this gives us We just have to put this in our calculator, and the answer would give us 0.0025 molar per minute. And this one here is our answer to the question, as it's asked us to solve for the average rate of reaction in terms of concentration of H2 consumed per minute. Another objective that will be included in the end of year exam is to calculate the value of KAQ, or the equilibrium constant, when the concentration of reactants and products are given at a constant temperature. Remember that KAQ is only applicable for a specific temperature. Let us look at the sample problem on equilibrium constant expression. So we have this equation. Now remember that in writing equilibrium constant, it is very essential that in the numerator we have the concentration of the product. So we have the products here, and we have the reactants in the numerators. Now for example, if we have the chemical equation A plus B producing, or another reversible reaction producing C and D, and we have here the coefficient of A is X, the coefficient of B is Y, the coefficient of C is W, and the coefficient of D is Z, then all of these components of the reaction are AQ, or gases, because remember that liquids and solids are not part, or does not affect the equilibrium constant, does not affect KEQ. So therefore we could write the KEQ expression of this example as the concentration of C raised to the power of W multiplied by the concentration of D raised to the power of Z divided by the concentration of A raised to the power X multiplied by the concentration of B raised to the power Y. Having said that, let us look at our reversible chemical equation. So since carbon here is actually solid, therefore it will not take part in the equilibrium constant expression. Therefore we will just have KEQ is equal to CO, carbon monoxide raised to the power of 2, because of this coefficient here, divided by the concentration of the oxygen gas. Since it doesn't have an exponent, it doesn't have a coefficient, therefore it wouldn't have an exponent. And if we're going to look at our choices, therefore E is the correct answer as the equilibrium constant expression of this example. Here is a sample problem on equilibrium constant. So we are given the balanced reversible reaction of sulfur dioxide plus oxygen forming sulfur trioxide, and we are asked to write the equilibrium constant expression in A. These values, by the way, here are the concentrations of the components of the reaction. So remember, in writing the equilibrium constant expression, we have only to consider aqueous, which are labeled AQ, and gases, which are labeled with a G. Anything that is labeled with L and S, or solid and liquid, are not part or should not be included in writing the equilibrium constant expression. So therefore, for this particular reaction, KEQ would be equal to the concentration of the products, that would be SO3, raised to the power of 2, mainly because of this coefficient over here, divided by the concentration of the reactant. So we have SO2 raised to the power of 2 because of this coefficient, multiplied by the concentration of oxygen. So again, remember, it should be the concentration of products over concentration of reactants. Moving on to part B, calculate the value of the equilibrium constant KEQ. So we have KEQ. Looking at the expression that we have in part A, so that means the concentration of SO3 raised to the power of 2. So concentration of SO3 according to the given is 0.65. Do not forget to square it. Divided by SO2, concentration of SO2, that is 0.42. And based on our expression in A, do not forget to square this particular concentration, multiplied by the concentration of oxygen, which is 0.18. And this is equal to 13.13. Next, which reaction is favored, forward or backward? Justify your answer. Since our KEQ is greater than 1, therefore the forward reaction is favored. Forward is favored. And this means as well that the products are favored. This means to say that if our KEQ is less than 1, therefore the backward reaction is favored, or the reactants are favored if it was KEQ is less than 1. But since it's greater than 1, then to answer part C, products are favored. Still another objective, describe and use the collision theory to explain why a collision between two particles is necessary for a reaction to occur. So for this point, it is because with collision that chemical bonds are broken and new bonds are formed. Now, why collision between two reacting particles do not always yield a product? And this is because not all collisions are effective. For an effective collision, reactants must collide with sufficient energy. This is to overcome the activation energy, and not only that, they should also collide with proper orientation. Again, they must collide with sufficient energy and proper orientation. And that concludes this tutorial. Once again, always remember, chemistry is easy with Mr. Jesse.